All right, this little section is probably one of the most important ideas or topics in chemistry. It's called molecular polarity, and determining if things are polar or not can be kind of difficult, but polarity gives things specific properties and explains a lot of what we see in chemical interactions. So molecular polarity can be determined based on their 3D shape. So we talked about bonds being polar in the last module. But in this module, we're going to talk about whole molecules being polar. Okay, and I kind of introduced that in the last module. We're going to get more into it here. So if you have diatomic molecules, so two atoms bonded together, they are polar if they have different electronegativity. So like HF is polar, right? F is way more electronegative than hydrogen. This is how we draw our dipole. This is how we show a partial positive. That's a delta plus. This is how we show the partial negative. That's delta minus, means it's a little bit negative and a little bit positive. So they will attract other things that are negative and positive, or ions and things like that. All right, now that's easy if it's just one thing bonded to another thing. Right? If it's more than two atoms, however, the polarity of a molecule depends on the polarity of those individual bonds, but also the shape or the molecular geometry. So for example, when I'm comparing CO2 to H2O, well, CO2 is a linear molecule, 180 degrees. This bond dipole would be pointing toward the oxygen because oxygen is more electronegative than carbon. So with this one, they are the exact same bond, they are the exact same size. So this vector, which represents this dipole, and this vector, which represents the dipole for this one, actually cancel out because they are linear. Okay, so if they're the exact same size and in the exact opposite direction, they cancel out. So while this carbon-oxygen bond is polar, the entire molecule of CO2 is non-polar because everything cancels out. It's very symmetrical. There is no area that is like hogging the electrons. Okay, so that would be a non-polar molecule overall. Whereas water, which has 4 domains, so this is actually bent. You have a bond dipole going from hydrogen to oxygen, and on this side, hydrogen to oxygen, and they are the same size, but they are not in the exact opposite direction. If you actually add these vectors together, you get this blue vector here called the molecular dipole. That's when your dipoles don't cancel out. You have what's called a net dipole moment. That means that the dipoles don't cancel out, and that molecule is polar. Okay, so this whole molecule actually has, since these arrows are kind of pointing up together, that means that toward the top, it's more electronegative. That's where the negative partial charge is going to be. And toward the bottom is where the positive partial charge is going to be. So this is the addition of these two vectors. Okay, and down here, just looking at the vectors, you can see they cancel out. This one goes in that direction. This one goes in that direction. It's non-polar. Here's a different example of a different molecule, BF3. If they are all, if you have a molecule that's got 3 things all exactly the same, so I have 3 vectors here, and you might be looking at those like, well, they're not in the exact opposite direction. And yes, that is true, but it's completely symmetrical and it's flat. So nothing is like pointing upward or downward. These are actually all going to cancel out as well. This is going to be non-polar. Because of the way that vectors add, this one is going to cancel out with the downward of these two, and these two are going to cancel out with the sideways. So what I want you to look at when you're trying to determine if something is polar, now if you know how to add vectors, add the vectors, but I want you to look at the symmetry and if there's lone pairs on the central atom, because first of all, these have to all be the same atom. Okay, for example, if this was like hydrogen and these two were fluorine, then this dipole, number 1, would not be the same size as 3 and 2, and it wouldn't cancel out. So the molecule has to be like symmetrical all around. If one of these is a lone pair, that's going to affect the shape, and that is going to affect it and cause it to be polar. Now, there's only really one instance in which a lone pair won't make something polar, and that's if it's square planar because it's flat and everything cancels out. But other than that, if you have a lone pair on the central atom, it's going to be polar. Okay, so example number 4 says determine whether the following are polar or non-polar. So I drew them. I've got PCl5 here. Okay, so this is all chlorines on the outside. I left off all of the dots on the chlorines. If you draw your Lewis dot structure correctly, there are no lone pairs on the center. And remember I said to look at symmetry and lone pairs. So there's no lone pairs on the center. These are all as far apart from each other as they can possibly be. It is a perfect trigonal bipyramidal molecule. It is non-polar. So you might be looking at these and we're like, well, remember, it's up and down and 3 in the middle. So the up and down cancel out. And then the 3 in the middle, like BF3 we were just looking at, also cancel out. Those 120s are going to cancel out as well. You know, if you draw H2CO, and I said that the C was double bonded to the O, so C goes in the middle, you got hydrogen. Hydrogen has to be on the outside. It can't be in the middle. If you look at these bond dipoles, this one is pointing up and the other two are pointing in and up. So overall, this molecular dipole is going to be pointing up. So it is polar toward the oxygen. So the oxygen is going to be a little bit negative, whereas the other side, the hydrogens are going to be a little bit positive. So this is polar. It is not symmetrical, right? I have hydrogen, hydrogen, and oxygen. Now, if it had been hydrogen, hydrogen, and hydrogen, that would be nonpolar. But since these are all different electronegativities, it does end up being polar. So you want to look at how symmetrical it is and if there are lone pairs on that central atom. So example number 5 says determine the molecular geometry around the central atom and state whether each of the following molecules are polar or non-polar. So I did a couple of these. I'm going to talk through SiF4 and then you should try A, C, and D. Okay, I drew SiF4 here. Make sure you draw a Lewis dot structure and count your valence electrons. This is completely symmetrical. There are no dots on the middle, so this one is going to be non-polar. So I would go ahead and pause it here and then try these other ones. Okay, so this one is bent. It's going to be polar. Anytime it's bent, it's going to be polar. This would have an arrow that points toward the sulfur. This one, CH2Cl2, we got a carbon in the middle. If you draw it this way, you might be like, oh, that looks symmetrical. Those are going to cancel out and those are going to cancel out. But you have to remember that these are 3D molecules and this is not flat. It is a tetrahedral molecule, meaning it has 109.5-degree angle. So if you draw it in 3 dimensions, you will see that actually the chlorines are close together. So you are not going to have them cancel out no matter which way that you draw it. So this is not going to be symmetrical because it is a tetrahedral molecule. So it ends up being polar. XeF4, this is kind of the exception I was talking about earlier. This is square planar, so it is completely flat. 90-degree angles, right? All these are the same, so that one is going to end up non-polar. Now, COSE looks like carbon dioxide. It's got double bond O, double bond SE. However, oxygen and selenium are very different in electronegativities. Oxygen is much more electronegative, so we're really going to have a dipole up here and really nothing down here. These are actually about the same. So they do not cancel out because they are not the same atom. They're not the same electronegativity. So this does end up being polar even though it's linear. So you have to look at the symmetricalness, yeah, the symmetry, and if there are dots on the middle. Okay, so the 3D and the lone pairs. Rule of thumb is if it's symmetrical with no lone pairs, then it's going to be non-polar, except for square planar.